Alright, today we're going to have a look at vertical resisted motion. So far we have done resisted motion, but we've only done resisted motion that's been going horizontally in a straight line back and forth, or horizontally in a single direction. Now, that's all well and good when we're talking about cars moving or balls rolling along things, but vertical resisted motion is a bit more tricky because it introduces another variable. So not only when you are rising or falling, not only is there some resistive force that is opposing your rise or a resistive force that's opposing your fall, but there's also gravity. Now, the resistive force always opposes motion, which means if you're moving up, the resisting force is going to be pushing down, or if you're going down, the resistive force is going to be pushing up. And that makes sense. That's based on Newton's third law, that every action has an opposite and equal reaction, even if it's by air or there's some sort of resistive force. But if I'm moving down, gravity is going to assist my moving down force, and the resistive force is going to stop me. So rising objects. So if an object is rising, we're going to take its starting point to be the origin, and we're going to measure upwards motion as positive. Now, really importantly with vertical resisted motion, since it's only in one direction, our first dimension that we talk about is always x. So even though we're moving up or down, we're going to treat it as x. The reason we don't treat it as y is because when we use y in variables, that's often implying that I've got an x and a y variable. So our first variable is always x, and this is just one-dimensional travel. So if an object is rising, yes, we're going to take its starting point to be the origin and measure upwards as positive. Now the two forces are the gravitational force, which is going to resist its motion going down, and also the normal resistance force. Now, as we saw last lesson, our resistive force is going to be kV, which means resistance is proportional to velocity, or kV squared, which means resistance is proportional to the square of the velocity. Now, if my object is moving up, now importantly, even though an object is moving up, we're not talking about rockets in this question. We're talking about objects that are moving up, and nothing, once they leave their starting point, nothing is propelling them up, which means there's no upwards force. So the velocity is going up, but then gravity is opposing this, and the resistive force is also opposing it, so they're both negative. So my two equations are minus mg minus kv, take out the negative, or minus mg minus kv squared, because my object's going up and both of these forces are opposing my ascent. Okay. Falling objects is a bit different. Now, again, when we're talking about falling objects, we're still going to treat it as an x variable because this is just one-dimensional travel, and again, when we're talking about one-dimensional travel, we deal with x. I guess if you really wanted to, you could use y, but it's not what we do. Now, again, we're going to treat its starting point as the origin. So we're going to treat downwards movement as positive because we care about how far from my starting point if I've fallen. So we're going to have the starting point as the origin and measure downward motion as positive. Now, the two forces that act on the object are the gravitational force and kV and minus kV squared. But in this instance, if I'm moving down, well, my velocity is moving down, but gravity is going to make me move down a bit faster. So my gravity force is kind of helping my downwards motion. So it's a positive because it's pushing me further down and I'm already moving down. But if I'm moving down, air resistance or some other force is going to be stopping me from moving down. Now, when I say stop, it doesn't literally mean that air resistance is stopping the object. We know that's impossible, that's not going to happen. But it is going to oppose the downwards motion and slow it down a tiny bit. Now, the reason that air resistance doesn't stop an object and make it float in midair, well, of course, it doesn't make sense, but the reason is what we're going to do next, and it's the idea of terminal velocity. So, an object continually can accelerate down and down and down and down, but eventually the resistance force of air resistance is going to be great enough that it stops it accelerating. So it's still moving down, but it's not accelerating anymore. And that's because the air resistance ends up equalizing the acceleration. Because remember, air resistance is a force, it's also, and remember, force is related to acceleration. So when the downwards acceleration force is matched by the equal and opposite air resistance force, it's still moving down, but it's not accelerating. And we say that it's maximum or its terminal velocity. So terminal velocity is a maximum velocity an object can achieve when falling. And it's different for every object. It's subject to how much air resistance the object experiences. It's subject to how aerodynamic the object is. It's not, however, subject to how heavy the object is, which is a common misconception. That's in fact why if you drop a pencil and a feather, or a bowling ball and a feather, they'll both hit the ground at the same time in space when there is no air resistance. So terminal velocity occurs when acceleration is 0. In other words, x double dot is equal to 0. Now note, an object can never reach its terminal velocity. It can only approach it like an asymptote. So I've got a brick weighing 1 kilo is placed on the surface of a lake and then released. And it sinks with an equation of motion x double dot is 10 minus kv squared. Something really important with this is if your equation of motion, specifically your equation of acceleration, if it's given, you're not going to prove it. Sometimes we might want to prove objects like this. We say mx double dot is equal to 10 minus kv squared. And then we're going to divide by the mass, 10 on m, minus k on m v squared. Now in this instance it's not actually going to matter because the mass is 1, but if the mass was anything but 1, when I divide by m, maybe it was 2, I'm going to get a 2 down here and a 2 down here, which no longer is the given equation. So importantly, the k that's given in this question has already factored in a division by m, and if we do it again, our k is going to be wrong. In fact, this k here, this constant here, is not going to be the same as this k here. Okay, so we're not going to prove it. So, terminal velocity occurs when acceleration is 0. Now, acceleration is x double dot, so 0 is equal to 10 minus kv squared. We're told the terminal velocity is 2. So that's going to make what? K 2.5. 10 divided by 4 is 2.5. So part 2, my equation of motion is x double dot is equal to 10 minus 2.5 v squared. Now this thing here is what we call the drag coefficient. And it's kind of like, you might, and it doesn't make sense, the higher this number is going to be, the more drag there is, and we call it the drag coefficient. In physics, you give it that symbol there. Mu. Okay, and we want to know how deep is the brick when it reaches 90% of its terminal velocity. So how deep is telling me I want x, I want displacement, and obviously we want to be able to substitute in terminal velocity, or 90% of it, so we want v. So I'm thinking, okay, which equation has v and x? That's v to v dx, which we haven't used that much, but we're going to use it a lot in vertical resisted motion. V to v dx is 10 minus 2.5 v squared. We're then going to divide both sides by v. So v to x is equal to 10 on v minus 2.5 v. And we want to integrate with respect to v because there's v's. V's are what this equation is in terms of. So we're going to have to flip it upside down. But before we can flip it upside down, we do need to make it a single fraction. We can't, or we can, but it's not as elegant to flip it upside down when it's not a single fraction already. So that's telling me that dx to v is equal to v on 10 minus 2.5 v squared. And we want to integrate this. Now the differentiation of 2.5v is 5v. So in an ideal world we want a 5 up here, but we've got to times this by 1 on 5. So if we integrate that, x is going to equal minus 1 on 5. That minus comes from this minus down here. ln of 10 minus 2.5 v squared plus c. Okay. Before we can actually answer the question, we do need to find this value of c. So we do know, well, I guess we're assuming that it starts at rest. If it's released on the surface of a lake, then yeah, it's going to be starting at rest. So when x is 0, remember, if an object is falling, we set its starting position as 0. So 0 is equal to minus 1 on 5 ln. If we put in 0 here, that's just going to die. So it's going to be ln of 10 plus c. So that means c is equal to 1 on 5 ln 10. So if we combine this is going to go first and that's going to go second. And if we use our log laws, we can simply get that this is 1 on 5 ln of 10 over 10 minus 2.5 v squared. And let's look at what the question was asking. How deep is a brick when it's 90% of its terminal velocity? Now its terminal velocity is 2, and 90% of 2 is 18 on 10, which is 1.8. So we're going to substitute in what v is equal to 1.8. So we might find x of 1.8. Type that into our calculator. So 1 on 5 ln of 10 over 10 minus 2.5 times 1.8 squared. So we get it's 0.33 meters. We're done. All right. Another one we're dropping it again. So dropping it, we're treating gravity in this instance to be positive, because if I'm dropping something, then gravity is going to be assisting its fall. So x double dot is equal to mg, or we might start with mx double dot is mg minus. Now, something that's going to be, they'll be very, very clear about this in the HSC, but in textbooks they're not as clear when they do this. Notice that in their velocity equation they don't have any m's, which is telling me that my integral is not going to have any m's in it. Now, because of that, what we're going to do is we're going to multiply the resistive force by 40. Now, technically we're not allowed to do that, but some textbooks do it just to make the maths easier. If you don't do it, you're just going to get an equation that involves m's in it, which technically, if you do some manipulation, you end up realizing that it is the same answer. But in the HSC, often they won't get you to prove the equations. They will give you this equation, and that's going to get rid of any inconsistencies in that. Now, because we've done that, we can cancel the m's, and we can say x double dot is equal to g minus v squared on 40. The HSC, and I'm going to make a couple of videos on HSC questions, will start here. They will tell you this equation, and that's going to get rid of any ambiguities in this whole m thing here. In this question, we're also told to assume that gravity is 10. Now, notice as well something that I haven't quite specifically mentioned is that since we're moving down, gravity is going to be positive, and as I'm moving down, there's a resistive force moving upwards that's opposing my motion. So that's a negative resistive force. Resistive force always opposes the motion. Go away. Okay. Now we want something that involves time and velocity. So that's telling me I want dv to t. dv to t, now we're told gravity is 10 minus v squared on 40. Now we need to integrate with respect to velocity because there's velocities here. So I do need to flip it upside down, which means I need to make it a common fraction. Okay, when I see something like this and I'm flipping it upside down, I'm thinking to myself partial fraction decomposition. So let's keep that in mind. Flip it upside down. Now, we have 400 minus v squared on the bottom. When you're in this instance, the two things that are going to come to mind are, first of all, logarithms, but second of all, partial fraction decomposition. Now, this one, unfortunately, is not a logarithm, because if you've got a v squared on the bottom, you need a v on the top, which we don't have. So we might realise that this is a difference of 2 squares. So it's going to be like that. And to integrate that, I'm going to say time is the integral of something over 20 plus v plus something over 20 minus v. I think it's going to be 1 with respect to v. Right, so if we put in negative 20 here, we're going to have 40 over 40 minus 20, 20 minus 20, so 1. And then if we put in positive 20 here, we're going to have 40 over 20 plus 20, which is 1 again. Nice. So this is going to be, integrate that, we get ln of 20 plus v. Integrate that, we've got that minus there. So minus ln of 20 minus v plus c. Now we've got, we can combine that. So 20 plus v on 20 minus v plus c. Let's actually see where we're headed. Right, so we've got e to the t's, we've got velocity to be the subject. So we do need to make v the subject. Now we know when time is 0, well, it's dropped through oil, so obviously when it starts, it's going to be at rest. So when time is 0, I thought I had another, I do, time is 0, v is 0. And I feel like that we're smart enough to be able to realise that that means c is going to be 0. It's quite obvious, but if you're not sure, if we put 0 here and 0 here, we're going to have ln of 20 over 20, which is 1, and ln of 1 is 0. So therefore time is ln of 20 plus v on 20 minus v. And we want to make v the subject, so we're going to raise both sides to the power of e. And then we're going to have a go at rearranging. So 20 plus v equals 20e to the t minus ve to the t. So plus that over there, we're going to have v e to the t plus 1 equals 20e to the t minus 20. And we might say v equals, let's pull out a factor of 20, 20 times by e to the t minus 1 over e to the t plus 1. Now we're thinking part 2 of the question we are going to have to integrate again, but this is not quite what we were after. So the trick with this, and it's a strange trick, but it's the only way that we can integrate this function is by doing this. So e to the t, we're going to have to plus 1, but then we're going to have to minus 2. So that's the same thing. Now this and this bit on the top is going to be 1, so 20, and I'm just going to say this is outside of 1 minus 2 on e to the t plus 1. And that's actually what we were after. Alright, part 2. We have to prove we've got x's and time. So our current question has got velocity and time, so we're going to make it nice and easy. We're going to replace it with dx to t, and that's equal to 20 outside of 1 minus. Now, let's kind of think in advance. We are going to have to integrate this. Now, I don't know how to integrate that at the moment, because I don't have the differentiation on the top. It's not tan inverse because there's no 2 there, so thinking, what else can I do? The trick with this, and once you see this trick, you're not going to forget it, but it is something you really are not going to think of initially. You're going to multiply every term by e to the minus t. So if we multiply this by e to the minus t, we'll add the indices, you get 0, so it's 1 plus e to the minus t. Really strange trick, but it does work because now the differentiation is now on the top. So this is 20, integrate this t. Now the differentiation of this is a minus e to the minus t, which makes this plus 2 ln of 1 plus e to the minus t plus c. Really strange trick to integrate that, but ends up being really easy. Okay. We need to find c. Now we do know that when time is 0, x is 0. So that's going to be x is equal to 20. That's going to be 0. E to the 0 is 1. So this is going to be 2 ln. 1 plus 1 is 2 plus c. So that makes c minus 20 times 2 ln of 2. Now you might wonder, why did I not make that 42 ln of 2? Well, when I go like this, up here, I'm actually going to factorize this 20 and put it inside here. So 20 outside of t plus 2 ln of 1 plus e to the minus t, close brackets, minus 2 ln of 2. So that this 20 here has gone to here, and we're just left with that there. Now we can just simplify this using basic log laws. So this is t plus 2 ln of 1 plus e to the minus t on 2. And that's what we were trying to prove. So that 2 has gone down there. Okay. Let's have a look at one more example. So here we now got something that's being projected upwards. So a ball of mass m is being projected vertically upwards. The acceleration acting against the ball plus air resistance is proportional to its speed. Find the time taken to reach greatest height. Now when we're moving up, if you're moving up, so my velocity is going up, you've got your weight force pulling you down, and also our air resistance, which is proportional to speed. So we're going to say mx double dot is equal to minus mg minus kv. Again, gravity's pushing you down, and the weight force, sorry, you're moving upwards, gravity's pushing you down, and the weight force is pushing you down. Not the weight force, sorry, the resistive force is pushing you down. So we might, for simplicity of the maths, put an m here. That's going to make the maths a bit easier. Do you have to? No, but it's going to make your maths just a bit easier. So we're going to say this is minus outside of g plus kv, and that's equal to, let's see what we want. We want time and greatest height. So when I see time and greatest height, when I hear greatest height, I think velocity being 0. So I want a d to t here. Now to integrate this, we're going to have to flip it upside down. So t to v is equal to minus 1 over g plus kv. Now to integrate this, in an ideal world, we want a times by k up here. So I'm going to have to put 1 over k here. Now we can integrate this. This is just minus 1 on k, ln of g plus kv plus c. Nice and easy. We're almost done. We just need to figure out this constant c and then evaluate. Now we know it initially has a speed of u. So when time is 0, its speed is u. So 0 is minus 1 on k, ln of g plus ku plus c, which means c is positive 1 on k, ln of g plus ku. Now if we have a go at combining this using our log laws, this one has a minus here, which means that's going to go on the bottom. So it's 1 on k, ln of g plus ku over g plus kv. That's our equation. We just got to now answer the question. So it says, find the time taken to reach its greatest height. Greatest height, back from our work with extension 1, projectile motion, occurs when velocity is 0. So we're just going to set that to be 0. 1 on k, ln g plus ku on g. Done. Okay, that's vertical resisted motion. Thank you.